Okay, section 10.2 is pretty darn important. It's the fundamental theorem of calculus. Oh my goodness, what could be more important than this? It's the fundamental theorem. So it is pretty awesome, actually. Let's get into it. So we've already learned about indefinite integrals. Another name for that is an antiderivative. And, you know, when you get the answer, what we call that is you get an antiderivative. So just to review, if we were looking for this, the antiderivative of 2x in this case, how do we do that? Well, this is when, you remember, you take the exponent, which is 1. First of all, you don't do anything with the coefficient, so we just keep the coefficient. Then we take the exponent, which is 1, and we make it 1 higher, so it's now 2. And whatever number we just wrote there, the 2, we also put that in the denominator. Then we put plus c, don't forget that, and then we simplify. So, in the first case here, the first term, we can cancel out the 2's. We get x squared plus c. This is an antiderivative, and it is our solution to this integral, indefinite integral. And if you tried it, like if you took the derivative of this, you'd get 2x, which is exactly what it says here. It worked. Okay, so now we're going to look at is a definite integral. What's the difference? With an indefinite integral, our answer was an antiderivative, right? X squared plus c. With a definite integral, it's more definite, right? The c is what makes it indefinite, because there's a whole bunch of things this c could be. It could be any constant, and it would still work. With a definite integral, there's no more c. The answer is just one number. There's only one answer that works. So the reason for this is because there's limits of integration. They're also called upper and lower boundaries or upper and lower bounds. So if you look, I've got the same question. The 2x dx is written here again. I've got that big S, which stands for sum. But now I have something new. I have these numbers right here. I have a 3 and I have a 1. Well, the 3 is the upper bound, or the upper limit, or the upper boundary. And the 1, of course, is the lower bound, or the lower limit, or the lower boundary. So with the 1 up here, the indefinite integral, the way you'd say that is the integral of 2x with respect to x. That's what the dx part is, right? With respect to x. The way you say this one is the integral of 2x with respect to x from 1 to 3. So I'm going to show you how this works. It starts off the same thing we did up here. You take the exponent 1 and you make it 2, so you get 2x squared. Put the same number on the bottom, 2, and plus c. Although you're going to soon see we actually don't need to do this, but I'm going to do it for now. And then, so far we have exactly the same thing. So we can simplify that and get x squared plus c, just like we did before. Now it's time to take these bounds into consideration. So the way you draw this, there's different ways to write this actually. I tend to do like just like a bracket like this. Some people do that. Some people just draw a line. I tend to put the closed bracket sign sort of. And you put the numbers here, 3, 1. Now the way you evaluate this is you're going to plug 3 into x and see what you get. And then you're going to take away whatever it is when 1 is plugged into this. So how am I going to do this? Let's do this. At 3, this amount, 2x dx, which is what we started with, what it equals is x squared, but we're putting 3 in there, 3 squared plus c. Well, we can simplify that. You get 9 plus c. Now, at 1, how much does this equal? 2x dx? It equals 1 squared plus c. So that's 1, because 1 squared is 1, plus c. And then what we do is we subtract. So we take the first one, the 9 plus c, and we subtract the second one, the 1 plus c. Now, what's going to happen to the c's? You're going to have c take away c. It's going to cancel out. This is going to happen every single time. And for this reason, you no longer need to worry about constants when it's a definite integral. If it's indefinite, you always need to be putting plus c. If it's definite, you don't need to. So all we're left with is 9 minus 1. Our answer is 8, right? We said the answer would be a number, and there it is. So let's try a couple more of these, and we'll do it faster. We won't write as much stuff down. So here's what we do. We need to take the integral of cosine x. Remember what that equals? If not, check your list of common antiderivatives. It is sine x. Now, we're not going to put plus c. Instead, we're just going to put our bracket sign or our line there and put the upper bound and put the lower bound. Now, we don't need to write all this stuff I did up here about at 3 and at 1, at pi over 2. Let's just do it. Let's just plug pi over 2 in here, so you get sine pi over 2. And then we're going to take away, remember the last step was to subtract. Might as well just get right into that. We're going to subtract. What are you going to subtract? We're going to subtract whatever the value is when you put 0 in there. Sine 0. When we do this, we'll get our answer. So sine pi over 2, that's sine 90 degrees. Well, that's 1. Sine 0 is 0. 1 minus 0 is 1. That's it. That is our numerical answer here. Okay, let's do a few more quickly. How do we integrate this? Raise the 2 up to a 3, so it becomes 5z to the third. Put the same number on the bottom. Raise the 1 on the z up to a 2. Put the same number on the bottom. And we're integrating in terms of z, so don't make it 3x. It's 3z here. And we've got our bounds. We have 1 and we have -2. So the first thing we're going to do is plug 1 into all this. Oh my gosh. Well, I'm going to put all this in brackets. If I put 1 in here, 1 cubed is still 1, and 1 times 5 is 5. I get 5/3 minus. If I put 1 here in square, you still get 1 times 7 is still 7. If I put 1 here, you just get 3. Take away. Oh no. -2 in here, cubed is -8, and times 5 is -40. Ooh, look at all these fractions. Over 3. Take away. -2 all squared, so that's +4, times 7 is 28, and divided by 2 is 14. That's nice, no fraction. And if you put -2 in here, you get 3 times -2, which is -6. So why don't we get common denominators for the fractions, which would be 6. So I'm going to multiply this by 2 and get 10 over 6. I'm going to multiply this by 3 and get 21 over 6. What the heck, I'm just going to keep that number there for now. Actually, I have a negative, so it's going to be plus, and I want the denominator to be 6, so multiply by 2, you get 80. And again, I'm going to keep these, but remember, it's take away a negative, which is plus, and take away negative, which is plus 6. I don't know why I put that in brackets. All right, so if I add together all the whole numbers, I have 3, 14, and 6, which adds up to 23. And then I have 10 over 6, take away 21 over 6, which is -11 over 6, plus 80 over 6. -11 plus 80 is 69 over 6. Which you could put it in the lowest terms. You could divide it by 3, and this will become a 2. So I know I'm kind of skipping steps. I'm going to get denominators of 2. Multiply top and bottom by 2 here, I get 46 over 2. And if I divide by 3, top and bottom, I get 2 and 23. And now I get my final answer, 2 on the bottom and 69 on the top. Okay, I kind of wish I hadn't done so many here. Feel free to skip this one if you want. So I think we have to rewrite this first of all. So keep this like that. Now 8, let's get this t up into the numerator. What would it be? It would be t to the -1/2 minus 12 t to the, look, we're cubing and also square rooting, so that's going to be 3 over 2. Now this is still in terms of t. Now we're ready to integrate this. How do we do it? Keep the coefficient the same, raise this up 1. If you raise that up 1, it goes up to 1/2, and you have to do the same thing on the bottom, 1/2. Minus, keep the coefficient the same, raise this by 1, so it's another 2/2, right? You get up to 5 over 2. And do the same on the bottom, put the same number on the bottom. And we're not putting dt anymore, we're putting our bounds, which are 4 and 1. Okay, let's simplify. Remember what happens here? If you have a 2 down here in a complex fraction, it actually comes up to the top. So you're going to get 16t to the 1/2, or 16 root t, over 1, no point in putting that, minus, the 2 comes up, so you get 24. You still have the 5 on the bottom. And when then we have t to the 5/2, so it's kind of like the square root of t, and then to the 5th power. And our bounds are 1 and 4. Oh boy. So here we go. First of all, I'm going to put 4 in here. So I get 16 times 2, right? Because square root of 4 is 2, minus 24 over 5. And I'm putting 4 in here. Square root of 4 is 2. And 2 to the 5th power is 32. Okay, that's when I plug 4 into it. Take away. Now I'm going to plug 1 into it. Square root of 1 is 1, and 1 times 16 is 16, minus 24 over 5. And I think you get 1 again, right? Square root of 1 is 1. 1 to the 5th power is still 1, so it just stays just like that. Sorry, but I have no room. 16 times 2 is 32. Oh my gosh, what kind of number is this going to be? 24 times 32 is 768 over 5, minus 16 minus 24 over 5. So 32 take away 16 is 16. And negative 768 take away negative, so that's actually plus. So we're adding 24 over 5. So that would get us to 744 over 5. Oh man, put this over 1. Get common denominators by multiplying by 5. You get 80 over 5 minus 744 over 5. You're going to get negative 664 over 5. All right. So a couple properties of definite integrals. If the lower bound and the upper bound are the same, then when you do the whole process, you're going to end up with 0. Now that should make sense, right? Because that means when you plug in, like pretend that, let's go back to this one. If it was pi over 2 and pi over 2, then we'd have sine pi over 2 minus sine pi over 2. You're subtracting the same amount, you're going to get 0. So that should make sense. And this one, if your bounds are b and a, upper bound b, lower bound a, and then you switch it, now it's going to be exactly the same as the previous answer, but it's going to be negative. And that should make sense too. It's kind of like the difference between going 3 minus 5 and 5 minus 3, right? One's going to be negative and one's going to be positive. And that's exactly what this is telling you. So nothing too earth-shattering here, but here's something that is earth-shattering. Feast your eyes on this, everyone. The definite integral, so we just talked about definite integrals when you have the bounds, of f, of some function, from a to b, right, those are upper and lower bounds, is defined by, okay, looks kind of similar to what we just did on the other side. What is this? We did this before. What is this? It's the total Riemann sum. It's the sum of all the rectangles under a curve. If you want to know the exact area under the curve, you don't have to do all those steps that we did before. You just need to get the definite integral. This is so exciting. The definite integral equals the Riemann sum. It's the same as the area under the curve. Oh my goodness. This is the fundamental theorem of calculus, part 1. There's 2 parts. If f is continuous on the interval, then all you need to do is get the antiderivative, plug in the upper bound, plug in the lower bound, and subtract them, and you've got the area, the exact area beneath the curve. In other words, the definite integral over an interval AB is equal to the antiderivative evaluated at B minus the antiderivative evaluated at A. I mean, I think you can just look at this and understand it, but here it is in words. So, we've actually done this question a bunch of times before. We found using rectangles an approximation of the area beneath the curve y equals x squared plus 1. When we did that, we got answers like 18 when we did right bound, we got 8 when we did left bound, and we got 11.75 when we did midpoint bound. Then we did the same question again when we did trapezoidal rule, and when we did that, we got the answer 12.5. And I told you actually that you would get closer with the trapezoids, but it's not always the case. In fact, this is a case where that's not the closest one. So let's see, let's get the exact answer, and you'll see we can do this so fast. All we need to do is take the antiderivative of x squared plus 1 in terms of x, with our lower bound being 0 and our upper bound being 3. Okay, so we find the antiderivative of x squared plus 1. How do we do that? The x squared becomes x cubed, and we divide by 3. Since this is in terms of x, our 1 just becomes x, and our bounds are 3 and 0. So the upper bound, if we put 3 in here, you get 3 cubed divided by 3 plus 3. Put all that in brackets. Minus the lower bound 0. 0 cubed, oh what the heck, I'll write the whole thing out, plus 0. Okay, figure this out, we got our answer. 3 cubed is 27, divided by 3 is 9, plus 3, minus 0 cubed is 0, divided by 3 is 0, plus 0. Oh, the answer is 12. Were we close? Well, 18 and 8 weren't great. 11.75 with the midpoint was, rectangles was actually the best. Trapezoids are pretty good. But this is the exact answer, and we found it so quickly. No drawing rectangles. No doing all this sigma notation stuff. I love this. It's one of my favorite things in calculus. All right, just to finish off, there is a second fundamental theorem of calculus. We've already mentioned it. We've already effectively talked about this. The idea is that the derivative, I don't know why there's that extra space there, derivative and the integral are inverse processes. So if you took the derivative of something and then integrated, you'd be back where you started. If you integrated something and then took the derivative, you'd be back where you started. And I think we're pretty clear about that by now, aren't we? Oh, by the way, there's one more thing I want to explain. Just let me really quickly sketch this. We went from 0 to 3, and it was x squared plus 1. So that's 1, and it goes all the way up to 10. So whatever, we get a parabola, we know what it looks like, right? Something like that. And what we found is the area underneath this parabola, underneath this curve, and down to the x-axis. So everything above the x-axis, all this area here is equal to 12. But let's go back. What this means at the bottom then, if we did that in this question, we'd have a cosine graph, would look something like this, where here's 0 and here's pi over 2, and we found that this area here is equal to 1. But what about in this last question here, where we end up with a negative number? What would that mean? Well, negative area means that the curve is below the x-axis, right? We've now got the area between the curve up to the x-axis. So here's actually the graph. It's a strange graph. And we were looking from 1 to 4 in that question. And you can see it's all underneath the x-axis. So we'd be looking at all this area in here. I can't even show you how low it goes. But we'd be getting all this area in here. And because it's below the x-axis, that's why we got that negative area there. Okay? Cool stuff. See you guys. Bye.